So in this video we're going to find the mean and variance of the log uniform distribution. Now the first thing we need to know is the PDF of our log uniform distribution. So our PDF, which is f of x, which is our random variables, and our parameters for this one are a and b. Very similar to the uniform distribution. Now this one is 1 over x times the log of b minus the log of a. So where our log here is log base d, natural logarithm. So this is our setup, that's the PDF, but there's some rules in the parameters for this distribution. So what we have is our b is larger than our x, which is larger than our a. So that's our range of distribution from b to a, but a must also be greater than 0. So as in here, log of 0, obviously that's undefined for all numbers, so therefore that's our kind of rules of where our parameters could be, and b could be as high as possible. Now the graph of this one is quite interesting. It's also known as the reciprocal distribution, and varying on what the parameters are for b and a, it follows a path something like this. Sometimes this point goes closer to here, sometimes it goes further out here, so you could also have it coming out this way, you could also have it coming out like this, depending on how the parameters are valued. Okay, so onto this video here, we're looking to find the mean and the variance. So first of all, let's look at the mean. So the best way to do that is through integration and integrating our PDF. So what we'll do is, let's just set our e of x, that equals, so integrated from a to b, that's our parameters. So a is our lower parameter, b is our upper parameter, and it's x times our PDF with regards to x. Okay, so now we've got our PDF here, so now we can just go straight in and integrate that for all values of a and b. So now our expected value is a to b, x times this one. So now we've got 1 over x. So now I'm going to write this log base d of b, I'm just going to write ln. So natural log of b minus natural log of a, and they're all with respect to x. Okay, so integrating this one looks pretty straightforward. These x's will cancel out. So now all we're doing is integrating a constant with regards to x. So that's just going to leave us with that multiplied by our x in terms of our integration. So that's going to equal x divided by natural log of b minus natural log of a. And then that's calculated from a to b. Okay, so now all we need to do now is plug in our difference between our parameter at b and our parameter at a. So now we've got, so this equals b over natural log of b minus natural log, just change that, natural log of a, and then subtract it when it's a, so that's a over natural log of b minus natural log of a. So we can simplify this up a little bit. So this could now be, our denominators are the same, so we can write this as b minus a over log of b minus log of a, and we can also write this as log of b over log of a. So let's write that down as our mean. So our mean, so that's e of x, that equals b minus a. Then in its simplest form, I'm going to write log of b divided by a. So that would be that in its simplest form. Okay, so next we're going to need to go on to find the variance. Now the variance, it's similar formula to this, but we're going to need it in two parts. So I'm going to go through that in a minute. Let's clear the board and let's get on with that. So now on to calculating our variance. So the mean in the last section, we had that as the integral from a to b of x f of x dx. Now we want to try and calculate the variance. So our formula for that is e of x squared minus e of x all squared. So these, being careful with this, these are not the same term. It's very important that this one is the mean squared and this one here is the moment, second moment, so e of x squared. So it's very important that the variance is come from this formula here in that order. And in previously I just calculated that the mean is this. So if e of x squared, I just square this term to get that, but now I need to find e of x squared. Now I can use this integral here where I use the mean to just write that as e of x squared and x squared f of x dx. So that's fully legitimate because I'm plugging in my x squared into here. So now all I need to do now is plug in my PDF and let's find our integral. So the integral from a to b of x squared times 1 over x, so now I'm going to write this in this term here, ln of b minus ln of a, and then dx. Okay, now what we can do is now just simplify this integrand and then bring our constant multiple out front, because this term here can be separated out because this is all multiplied, and then we'll have a nice easy integral for us to look at. So we've got x squared divided by x will just come out to be an x. This term here will cancel. So now this will come across and this will go over here. So that equals 1 over log of b minus log of a. Then the integral from a to b of x dx. So that won't change. The integral of this, nice and straightforward, is just x squared over 2. So now I can multiply this by x squared over 2 to give me my answer. So now I've got x squared divided by 2 times log of b minus log of a, and that's calculated from a to b. Okay, so now wherever I see an x I plug in or an a or a b. So at b I will subtract the value from when it's at a. So let's have a look at that. So now I've got b squared over 2 ln b minus ln of a minus, so now just plug it in the a squared, I've got a squared over 2 ln of b minus ln of a. And that there is our e of x squared. So we've not actually calculated the variance just yet, we've just got our second moment. So now what we need to do now is bring this up top for our e of x squared, and then what we can do is we can start to square this term and see if we can make our final conclusion as to what the variance will be. Now my e of x squared term is here. Now I can see there's a little bit of simplification I can do that and make it look a little bit similar to this one. So let's do that. So b squared, denominator is the same, so I've got b squared minus a squared. Then I write it in this form. I've got 2 times the natural log of b over a. So that will be the same term as we have there. Okay, now here I've got my e of x squared term to calculate, so that's this term. So let's try and calculate that here. E of x squared, that's now b minus a over the natural log of b over a all squared. Okay, now b squared minus a squared is not the same as b minus a all squared. B minus a squared is b squared minus 2ab plus a squared. So that's not going to be the same as that. So we can't amalgamate those terms anyhow. And here we've got ln b over a and ln b over a squared. So let's just see if there's anything we can do with that. So we've got b minus a squared. Then this term squared, I've got log of b over a all squared. Okay, so this one here, I can't really simplify it very much to try and make a similar denominator with my e of x squared. So I'm going to declare my variance using this term and this term. So my v of x, that's my variance, is this term here. So that's my e of x squared. So b squared minus a squared. So I'll put that in brackets. I could also say that as b minus a times b plus a, but I'm just going to leave it like that for now. And then I've got the natural log of b over a. And then I'm going to subtract this term here for my e of x squared. So that's minus b minus a divided by the natural log of b over a and all squared. Okay, so that's going to be my declaration for my variance. And this I'm going to call my expectation. So that's my mean. So that's my two solutions for the log uniform distribution. Okay.